In today's class, we are going to start with chapter 2, numbers and sequences. First, we are going to start with the topic Euclid's division lemma. Let us see what does the Euclid's division lemma states. Let A and B be positive integers. Then there exist unique integers Q and R such that A equals to BQ plus R, where R varies between 0 and B, whereas 0 is included but R is not included. So what does it state is, we have two positive integers A and B. Positive integers means it starts with only 0, 1, 2, etc. it goes on. Then there exist unique integers Q and R such that it is written in the format A is equals to BQ plus R. What is this A in this Euclid's division lemma is, it is a dividend and B is a divisor, Q is a quotient and R is a remainder. Let us see with an example. If I want to divide 9 by 2, what will we do? We have to choose 4 2s are 8, balance will be 1. So now we will see in this, 9 is nothing but dividend, 2 is nothing but divisor, 4 is nothing but quotient and this 1 is nothing but remainder. This is what is represented as A equals to BQ plus R. Dividend, divisor, quotient and remainder. So first is example 2.1. We have 34 cakes. So total we have 34 cakes. Each box can hold 5 cakes. Only how many boxes need to pack and how many cakes are left unpacked? We need to find this. So in a simple way, what can we do is, for us the total number of cakes, it is given as 34 and what they are asked to find, each box can hold 5 cakes. So divided by 5, 6 5s are 30, balance 4. This is how we simply find out. But we have to express this in a Euclidean division lemma. Let us see how to express this in a Euclidean division lemma. So total number of cakes given to us is 34. Which we represent it as a dividend A. Next, what is given to us is, each box can hold only 5 cakes. Number of cakes in each box, which they gave it as 5, which is 5, and this 5 we express it as divisor according to the Euclidean division lemma. Divisor is denoted as B, which is into. Now what we have to do is, next we have to write the number of boxes, that is the total number of 34 cakes, each box can hold 5 cakes. So how many number of boxes we need, we are going to do. So number of boxes, we got it as 6 and this is quotient, which is represented as Q, plus we have the remainder as 4. Remainder as 4 means the number of cakes left unpacked, which we got it according to the division 4 and which we represent it as a remainder. Now let us see. A equals to BQ plus R is the Euclidean's division lemma. A given to us is 34 and the divisor given to us is 5. Quotient we got it as 6 plus remainder is 4 we got. Now if you simplify the right hand side, we will get the left hand side. 5 6 are 30, 30 plus 4, 34. So this is how we express in a Euclidean's division lemma. So now we are going to see generalized form of Euclid's division lemma. It is also the same as Euclid's division lemma, which is let A and B be two positive integers then there exist unique integers Q and R such that A equals to BQ plus R. It is same as the Euclid's division lemma. What is the only difference is the R value varies between 0 and mod B. And we all know that A equals to B plus Q, A is a dividend, B is a divisor, Q is a quotient, R is a remainder. What does this represent is the remainder value must vary between 0 and modulus of B. We all know what is modulus of B. If the B value is negative also, if we take the modulus, we should consider only the positive value. So, for example, if the B value is minus 5 means within the modulus it will become plus 5. So, R value must be less than plus 5. So, this is what this inequality represents. Example 2.2, what we have to find in this problem is, we have to find the quotient and remainder when A is divided by B in the following cases. We have to divide A by, when A is divided by B, using Euclid's division lemma, we are going to solve this. So, the first problem given to us is A value is minus 12 and B value is 5. We are going to solve this using Euclid's division lemma. I am writing it as an abbreviation, Euclid's division lemma EDEL, which gives us is A equals to BQ plus R, where R ranges between 0 and mod B. So, according to the values given in this problem, the value of A is minus 12 and the value of B given is 5. We need to find the quotient and remainder. Okay, so now in this problem, if you see, the A value given to us is in negative value. If the dividend is in negative value, any one of this value, either divisor or quotient must be negative. Any one of this must be negative. The divisor given in this problem is positive. So, we have to choose the quotient value in negative. And also one more thing we have to keep it in mind is, when this is a negative value, the product of these two, that is this output must be greater than minus 12. So, here it is 5. I already told you any one of these must be negative. So, if I choose 2, 5 into 2 minus 10, which is less than 12. So, we shouldn't choose that. We have to choose 5 minus 3. 5 into minus 3 minus 15. So, the value 15 is greater than 12. So, we have chosen in such a way. Now, we have to choose the remainder. How to choose the remainder is, see, the dividend given to us is minus 12, but we got the value as 15. Okay, so the difference between 12 and 15 will be the remainder. 15 minus 12, 3. Okay, if you solve the right hand side, we should get the left hand side. 5 3s are 15, minus 15 plus 3 will give us minus 12. So, hence we have completed. For the first problem, Q value equals to minus 3 and R value is equals to 3. Second subdivision is A is 17, B value is minus 3. According to Euclid's division lemma, A equals to BQ plus R, and where R values varies between 0 less than or equal to R less than modulus B. A value given is 17 and B value given is minus 3. We have to find the quotient and remainder. If you see in this problem, the dividend value is positive. Therefore, this value should give us the product of these two should give us a positive value. Already we have a negative over here. So, definitely we should choose the minus symbol here. Okay. So, next what we have to do is, for the previous problem I told, if the dividend is in minus, we should choose this product value should be greater than the dividend value. In this problem, the dividend value is positive. So, we must choose this value accordingly, which is less than 70. What can we choose? We can choose 5 3s are 15, minus into minus will become plus, 5 into 3 15. So, 15, this itself we got 15. In order to get 17, if we add 2 to this, we will get the 17. So, quotient value is minus 5 and the remainder value is 2. And in the third case, A equals to minus 19, B equals to minus 4. According to Euclid's division lemma, A equals to BQ plus R, where R varies between 0 and B. Okay. So, now in this problem, A value is given as minus 19, B value is minus 4. We need to find Q plus R value. Okay, so as I already told you, if this is dividend is in a negative value, any one of this value, that is either B or Q, it should be in a negative value. Already B is in negative value, so we have to choose only the positive value over here. And also one more thing I told you, if the dividend is negative, the product of these two terms must be greater than 19. So I should choose here 5 because 5 4s are 20, which is greater than 19. I chose accordingly. Now 5 4s are 20. What is the difference between the 19 and 20? There is only one number, which will be the remainder. So in this problem, Q value equals to 5 and R value equals to 1. Okay. Example 2.3. What we have to do is we have to show that square of an odd integer. Square of an odd integer is of the form 4q plus 1 for some integer q. We need to show this. So what will we do is, first I will consider the value of x is equals to 2k plus 1. Why am I considering 2k plus 1 is, we have to show that square of an odd integer. So I am considering some odd integer as x as 2k plus 1. Why is it is 2 into any value will be the multiples of 2. Multiples of 2 means definitely is an even number. So adding 1 to it will give us an odd number. Therefore, in general, we are considering x is equals to 2k plus 1. What it is square of an odd integer is of the form 4q plus 1. So, therefore, what we have to do? We have to square x term. So, if I square it on the left hand side, I should also square it on the right hand side. Doing it so, x square is equals to 2k plus 1 whole square. X square is equals to, what we have to do in the right hand side is, we have to use a plus b whole square formula to expand this. A plus b whole square is equals to a square plus b square plus 2ab. So, a value is 2k and b value is 1. What is 2k squared? 4k squared plus b square value is 1 plus 2 into a into b is 2 into 2k, 4k into 1. So, which will give us 4k. Let me write it in an order. So, 4k square plus 4k plus 1. Next step, what am I going to do is, I am going to take 4k common from the first two terms. So, 4k if I take in common, I will get k plus 1 and this plus 1. Now, what am I going to do is, I am going to consider this k into k plus 1 as an integer q. So, we can replace this k into k plus 1 as q, which is equals to 4q plus 1. This is what we are asked to prove, hence proved. Next we are going to solve the example using the Euclid's division algorithm. I will tell you the process of a Euclid division algorithm while solving this problem. You will understand more clearly. What is the problem given to us is we have to find the HCF. HCF is nothing but highest common factor of two given positive integers. The two given positive integers are a equals to 273 and b equals to 119. Such that a is greater than b. Why am I mentioning this in general is, while using Euclid's division algorithm, the a value must be always greater than b. If the a value is greater than b only, then we can use the Euclid's division algorithm. Let us solve this problem using the Euclid's division algorithm, and for that we will get the help of Euclid's division lemma, which means a equals to bq plus r. We are going to get the help of this equation. Now a value given to us is 273 and b value is 119. We have to find the quotient and remainder. 273 divided by 119. Let us take 119 into 2. What will we get? 2 9 2s are 18. 1 balance, 2 1s are 2. 3 2 1s are 2. So 2 times 2 38. 13 6. So 5 3. The quotient is 2. So 119 into 2 plus the remainder is 35. Okay. So what is Euclid's division algorithm is? We have to proceed Euclid's division algorithm until the remainder becomes 0. Here the remainder is not 0. So we have to proceed. Next step, this 119 will become a dividend and this 35 will become a divisor. So this is how we have to proceed the Euclid's division algorithm until we get the remainder as a 0. Now we have to divide 119 by 35. So let me choose 35 into 3. 35 into 3, 15, 1, 9, 10. So 3 times 105, 4, 1. 35 into 3 plus 14. So again if you see, the remainder is not 0. We have to again proceed the Euclid's division algorithm. Now what it is this 35 will become a dividend and 14 will become a divisor. Now we have to divide 35 by 14. So what is the quotient we can choose? We can choose 2, which is 28. So 14 into 2 plus the remainder is 7. Again if you see, the remainder is not equals to 0, we have to proceed. Now we have to consider 14 as a dividend and 7 as a divisor. Choosing it, so what will we get? 14 divided by 7, 2 times 14, 0. Okay, so 7 into 2 plus 0. Now we got the remainder as 0. We can stop it here. So now we are asked to find HCF of two positive given numbers. What will be the divisor over here is, when we get a remainder as 0, at that point what is the divisor we have? 7. So HCF of 273 and 119 is 7. So this is how we proceed with Euclid's division algorithm. Example 2.4, highest common factor of 210 and 55 is expressible in the form 55x minus 325. We have to find the value of x. What it is given is, if the highest common factor of 210 and 55 is expressible in the form. So first we will find the highest common factor of 210 and 55. Next we have to express that value with 55x minus 325 to find the value of x. Okay. So a value is 210. Why we are considering a value as 210 is, among these two the greatest value is a, and also for using Euclid's division algorithm we should use the value of a must be the greatest value. B equals to 55. Expressing this in the Euclid's division lemma form, a equals to bq plus r. A value is 210, b value is 55. We have to find q and r. So 210 divided by 55. I will choose 55 into 3, 55 into 3, 15, 1, 15, 16, 165, 10, 10, 45. So 55 into 3 plus 45. Now the remainder is not 0. Next step what we have to do, 55 will become a dividend and 45 will become a divisor. Now again we have to divide 55 by 45. What will we get? Choosing 1, 45, 10. So 45 into 1 plus 10. Again the remainder value is not equals to 0. What we have to do? We have to choose 45 as a dividend and 10 as a divisor. So 45 divided by 10, we can choose 4 times 40, remainder is 5. So 10 into 4 plus 5. Again the remainder is not equals to 0. Now we have to choose dividend as 10 and divisor as 5. So 10 divided by 5, 2 times 10. Now the remainder has become 0. This we can express it as 5 into 2 plus 0. When the remainder becomes 0, in that step the divisor will become the HCF of the two numbers. So HCF of 210 and 55 is 5. Okay, so we have completed the first step. Next, what it is given is the highest common factor of 210 and 55 is expressible in the form 55x minus 325. So this is 5. So 55x minus 325, which is equals to 5. Next, what can we do? 325, if it goes to the other side, it will become positive 325. So 5 plus 325, 55x, which is equals to 330. So 330 divided by 55, I can choose 55 into 6 because 6 5s are 30, 3, 30, 33. So 6 times 330, 0. Therefore, x value equals to 6. Next problem is find the greatest number that will divide 445 and 572. What we have to find is the greatest number that will divide both 445 and 572. Whereas that number, if it is divided by 445 and 572, it gives the remainder 4 and 5. So for 445 it leaves the remainder 4 and for 572 it leaves the remainder 5. What shall we do now is, first we will reduce the remainders from this number and we will use the Euclid's division algorithm to find the greatest number that will divide both 445 and 572. So first step what we are going to do is 445 minus 4, which will give us 441, and 572 minus 5, which will give us 567. Among these two, 567 is the largest number compared to 441. So that should be considered as the value of A. We are going to get the help of Euclid's division lemma, which is nothing but A equals to BQ plus R. A value here it is 567 and B value, that is divisor, is 441. We have to find the quotient and the remainder. Using Euclid's division algorithm, we will find the value. So 567, if it is divided by 441, I can choose only one times. So 441, 6, 2, 1. 441 into 1 plus 126. Next step, the remainder is not equals to 0. Therefore, we have to choose the dividend as 441 and the divisor as 126. 441, 126. I am going to choose 126 into 3, 18, 6, 7, 3. So 3 times 378, 11, 3, 13, so 63, 126 into 3 plus 63. Again the remainder is not equals to 0. We have to proceed in the same step. Now the 126 will become a dividend and 63 will become a divisor. So we have to divide 126 by 63. So by multiplying 2 with 62 we will get 126. So 62 into 2 plus 0. Now we got the remainder as 0. So when the in which step we got the remainder as 0, in that step the divisor will be considered as the HCF. When the remainder becomes the 0, in that step the divisor will be the largest number, that is highest common factor. So HCF of 567, 441 is 63. So 63 is the greatest number that divide 445 and 572. That we can also cross verify. I will divide 445 by 63. It must have to give the remainder 4. If it gives, then my 63 value is right. Again 572 divided by 63. If it gives me 5, then the steps we used to find was right. So 445 divided by 63, let us do it. So 63 into 7, 21 to 42, 44. So 7 times 441, it gives the remainder 4. So that is what is mentioned in the question. So the 63 we found as the greatest number is right. So next what we have to do is, we have to find the HCF of the 3 numbers 396, 504, 636. So in this problem, 3 numbers are given to find the HCF. So in such cases what we have to do is, first we have to find the HCF for first 2 numbers, then we will do it with the third number. So if I consider the first 2 numbers, among these 2, this is the greatest value, which I should consider it as the value of A, and this I should consider as the value of B. Let us do it. So A equals to BQ plus R. A value I am considering it here, it is 504. B value is 396. We have to find the quotient and the remainder. So 504 divided by 396, it will go with only one time. 396, 8, 0, 1. So 396 into 1 plus 108. The remainder is not equals to 0. Then what we have to do? This will become a dividend. 396 and 108 will become a divisor. 396 divided by 108. I will choose 108 into 3 times. So 8 3s are 24, 3. 3 times 324, 2, 7. So 108 into 3 plus 72. Again the remainder is not equals to 0. We have to proceed. Now 108 will become a dividend and 72 will become a divisor. So 108 divided by 72, we will choose 1 times. So 8, 6, 3. 72 into 1 plus 36. Again the remainder is not equals to 0. We have to proceed. 72 will become a dividend, 36 will become a divisor. So 72 divided by 36. So 2 times 72, 0. 36 into 2 plus 0. Now we got the remainder as 0. The divisor is the highest common factor of 396 and 504. So HCF of 396, 504 is 36. Next step what we have to do is, we found the highest common factor only for the first 2 terms among the 3 terms. Now next we have to find the HCF between 36 and 636, which will give us the HCF of all the 3 numbers. So again among 36 and 636, 636 is the largest number. So in this we are going to consider the value of A as 636, which is equals to the value of B is 36. We have to find the Q and R. 636 divided by 36. So what shall we do? 1 times 36, 7, 2, 6. 36 into 7 times 2, 4, 21, 25. So 7 times 252, 4, 2. 36 into 17 plus 24. Now the remainder is not 24, we have to proceed. 36 will become a dividend and this 24 will become a divisor. So 36 divided by 24, 1 times 24, 2, 1. 24 into 1 plus 12. Next again the remainder is not equals to 0. We have to consider the dividend as 24 and the divisor as 12. 24 divided by 12, 2 times 24, 0. 12 into 2 plus 0. So the remainder has become 0. The divisor in that step is 12. So the HCF of all the 3 factors are 12. HCF of 396, 504, 636, which is equals to 12. So this is how we find the HCF of 3 numbers.